Okay, looking at the quiz questions. Once again, scores look much better on this one. When is momentum conserved for a cannon and cannonball system? So it's the system of the cannon and the cannonball. And the options were always from before firing until the ball hits the ground. That one is not correct because you're going to have a net external force acting on that cannon. Also, you're going to have air resistance on the ball. And if the net external force is not zero, then momentum will not be conserved. But initially, before you fired it, it was stationary, so momentum stayed at zero. And the instant you fired it, the cannon recoils and the ball moves forward in virtually no time, so it's still conserved at that instant. But as soon as that instant's over, then the ball is going to start slowing down and the cannon's going to start slowing down. So it's going to be B. And I think everyone got that. No? Well. Number 2, a conserved quantity. What does it mean if it's conserved in physics? Doesn't change. Number 3, faster moving molecules correspond with higher temperature. And finally, a bowling ball attached to a rope is held up to your chin and released from rest. When it comes back, it doesn't hit your chin again. Why not? C, air resistance removes some of the energy. All right, now going to, I don't know why I did that. It's in this program. So we're going to continue talking about fluids. Remember last class period when I wanted to get my demonstration, I couldn't find it? Apparently I'm just blind because after class I went and opened the door and said, now where is it? It was sitting right there in the first place I had looked. So this is my demonstration. It's just a suction cup. Now this isn't your typical looking suction cup, but it illustrates the purpose. You have this nice piece of rubber with a handle so I can manipulate it. And you see I put it on here and I can easily slide it off the desk. But if I put it on here and I lift up, it's not so easy. When Nathan was doing it, I think that the rubber actually stretched up here to allow air in. The way these work, well, and so here's what I usually do. Pick up this piece of metal. Slide it off just fine, but lift it straight up as it lifts up. Now the big question is, what's holding, when I lift this up, what's holding them together?
The lack of air in between them.
Okay, Hosanna's exactly right. It has to do with the lack of air in between them. And actually you can tell that it's leaking a little because this keeps moving up, which means it's going to drop in a minute. There we go. So that's why Nathan and I are now able to lift it up because it's no longer good sealing here. Which I'm not going to fix. So we have air pressure. How big is the air pressure? 14.7 between friends, let's just call it 15. 15 pounds per square inch. So that means if you take my hand, the top of my hand measures, let's say 8 inches by 4 inches, so about 32 square inches. That means air pressure is pushing down the top of my hand 32 times 15. Well, what's 32 times 15? So let me punch that up just real quick, just to get a number. $480. So there's 480 pounds of force pushing down on my hand because of the air. How is it that I am so burly I can hold my hand out here with that much force pushing down? Is what? Can you explain what you mean by all relative? Well, I have 480 pounds of force pushing down on my hand. But I also have 480 pounds of force pushing up on the bottom. Remember, the pressure is always pushing into the surface. So it's pushing down on the top and pushing up on the bottom. Since it's 480 pounds pushing up and 480 pounds pushing down, the net force due to air is 0, or very roughly close to 0. I mean, it's really close. So that's not a problem. But if I were to put my hand down here on the table and I was able to get all of the air out from between my hand and the table, then I wouldn't have that upward force, and I would have to have 480 pounds to lift it off the table. Obviously, I don't get the air out of there when I put my hand on there. It may seem like it, but you've got grooves and whatnot in your skin. There's plenty of place for air to slip in and out. So then that comes to our suction cup here. So this here is just a flat piece of rubber. I put it on here, and it kind of forms a seal. Not very strong because I can slide off easily. So there is air under there, but it kind of forms a seal. When I lift up, I'm lifting up at the center. And so when I lift up at the center, it creates a cavity in the center. And the pressure in that cavity gets much lower real quickly because there wasn't much air, and it's got to spread out through that cavity. So when I lift this up, it creates a really low pressure underneath the suction cup. So because there's a really low pressure underneath the suction cup, that means that this thing here still has air underneath it that's sitting on the table. Once again, it doesn't seem like it, but it does. And so you have air pressure pushing up. Now this is a pretty big plate, right? And so you take that 15 pounds per square inch multiplied by the area of this plate. That's how much force is pushing down on the top and how much is pushing up on the bottom. But when I put this on, let's say the air pressure underneath this is, now let's just go to 1 pound per square inch. That would be 14 pounds per square inch different than the pressure underneath, which means I would still have, for the area underneath my suction cup down here, 480 pounds pushing up, but I would have 465 pounds, I would have 32 pounds pushing down. So 480 up, 32 down. There's a net upward force due to air pressure on this. That's like 448 pounds. So right, it's going to be going up because of the air pressure. In fact, the pressure in here is not going to go to 1 pound per square inch. It's going to go down to the right and bounds so that it holds it up in balance rather than pushing my hand up. I blame my son for working so hard to make it so he could get it off. Either that or age of this thing. So that's how suction cup really works. You get the air out of there, as Hosanna said, so the pressure underneath the suction cup is lower. So when you actually buy a suction cup, it doesn't look like this, right? It's got a shape that goes up in the center and down. You put it on and you push it on, so it's pushing the air out of the center. And then because of its arched shape, it pulls itself back up, so it immediately lowers the pressure underneath, so it holds itself on. So you can't just slide it off like this, because it's lowered the pressure because of its shape, so that it's holding on tight. So what holds the suction cup on ultimately is the air pressure outside pushing in, and not having the air pressure inside pushing out. Totally cool, right? Because it's physics. What is physics if not cool? It's cool. All right. Why do we have water towers like this in different municipalities around the country? So what?
They have water.
You can have the water underneath the ground and still have water. Why do they have the tower?
So
I mean, it is.
To create water pressure.
Okay, so gravity can be used to create water pressure. So they pump the water up there and it's stored up there, and you have a head of pressure, that's what we call it, that is going to be the pressure built up by having that water up there. Now, when I was in Africa, we had a little water tank just on top of our house. How do you suppose the water tank on top of the house compares to this? Yeah, there wasn't much water pressure in our house. So the water pressure is built up. I got to change the color because you couldn't see that. Because of the pressure difference in these elevations. Well, what did I tell you causes us to have a pressure, like an air pressure? Pressure lower in Colorado than it is here.
Elevation.
Okay, elevation because it's the weight of the air above you. So if you take a column of air, or let's take a column of water here. So here's a column of water of height h. Then the weight of the water in there is going to be force of gravity equals mg. But the m, the mass is going to be the mass of the water. And we're like, how do I calculate the mass of the water? Well, here's going to be the first place where I use density. From last class period, we had density defined. Density is the mass per unit volume. So density, and we use for density a symbol that you have to have explained or you don't know. Density is the Greek letter R, rho. And that's the mass divided by volume. So if I want to have the mass, water, we know the density of water. It's 1 gram per centimeter cubed. So I can find the mass by solving this equation for mass. So to get mass by itself, I'm going to have to multiply by V, multiply by both sides by V, and the mass is density times volume. And now comes some geometry. The volume of that cylinder is the area of the cylinder times the height. That is the area of the circle of the cylinder times the height. So volume is equal to area times height. So this is density times area times height. So I'm going to put this into here, and then pressure, the pressure difference is equal to that force of gravity divided by area, because pressure is defined as force divided by area. And what's going to happen with those areas? They cancel. And so the pressure difference is equal to the density of the fluid multiplied by the acceleration of gravity multiplied by the height. So the higher that tower, the higher the water pressure. And so you build that tower high enough and you get a high water pressure, and then you can use that pressure to distribute the water through the city. Now, that's not going to work well for a large city because you have too much water you need to distribute. You need to have a huge tower up there. And so in that case, then they're going to use a pressurized system with pumps to keep the pressure. For something like this, they just have a pipe that they slowly pump the water up and then let gravity pump it out. Question, Hannah?
So these are only in like smaller towns?
They're generally these days, I think, only in smaller towns. Just because, if you have a town of 1 million people, there's huge amounts of water. You either have to have a whole lot of those towers or an enormously sized one. And for efficiency, it's going to work better to have just a underground water supply that you then pressurize into the pipes.
Okay, second question. How do they know where to place these?
Yeah. I would guess it's just based on demand, because when you have water flowing through a pipe, you're going to have some pressure losses as it goes through the pipe. The pressure loss has to do with the length of the pipe as well as the diameter of the pipe. And so they want to use bigger pipes to have less pressure loss and have the pipes shorter in distance from the source. So you would ultimately want to try to find the central location so you have the smallest distance. Something that probably makes a lot of sense, since the water pressure is caused by the water up here, if I had a hose out here that was tied to that and I point it straight up, in a perfect world with no pressure losses, how high do you suppose it could shoot the water up?
Are you talking about a geyser?
Well, coming from a hose rather than...
Because when you hold a hose up, it doesn't go, if you hold it up, it doesn't go very far unless you push your thumb on it and...
to get higher speed.
Yeah.
But there's no way that you could have the water go higher than it started up here. That's the highest that you could shoot it. Because you had gravitational potential energy, comes down here to make the kinetic energy, comes back up here, turns back into gravitational. So if you have a fire in this town and that's their source of water and they have no booster pumps, they're not going to be able to lob water higher than the height of that. So if you live in a building taller than the water tower in your city, you can't just open up a fire hydrant and splash water at the top. Now, fire trucks have pumps to increase the pressure so that you can pump higher, but there's still a practical limit to how much pressure you can put in those. The fire hoses will break. And so the height that they can make it go to is limited.
Is that hydrant pressurized or is that hose pressurized?
Well, if you're taking it out of a hydrant, then it's pressurized with whatever the city is supplying. And so I was saying, if it's this example, it's pressurized to the pressure that's coming out of that. What we do, I used to be in PUC's volunteer fire department. We connect a hydrant directly to the truck. We fill the truck from the hydrant, low pressure, high flow. And then from the truck, then we have a pump that raises the pressure that goes out to the fire hoses. So the fire hoses have the appropriate pressure for the nozzle and where they are and whatnot. And there's calculations that are done to determine what the pressure needs to be at the truck for them out there. So they take into account, you're going to have this much pressure loss per foot of hose, and we have this much hose connected. And, they actually calculate it out. It's not just seat of the pants, give me more pressure. Okay, here's a question for you that might be confusing or might not. Does a 3 meter deep lake or a 6 meter deep small pond exert more pressure on a dam? So which one's putting more pressure on the dam? This one here that's 3 meters down or this one here that's 6 meters? Now this one here has lots and lots of water. So lots of shallow water. This one has a little amount of deep. So to make sure it's really clear, the one on the left has more mass, less height. The one on the right has less mass, more height.
More height.
Okay, Hosanna says more height. Can you back that up?
Yeah, because so you have more height, so that means that there's more pressure in the pond instead of like a bigger one because at the lowest part there's more water pushing it down.
She's absolutely right. Yay! She's absolutely right. The pressure, right, we just did that calculation and the area canceled out. It was only the height that mattered, not the total mass of the water. And so the dam that's holding up this 6 meter deep pond has to be stronger than the dam holding up the miles long but only 3 meter deep lake. Because the pressure, the force per unit area, only depends on the depth of the water, and then the force it puts on the dam is going to be, the size of the dam times the pressure, or the area of the dam times the pressure.
How do you find the pressure that's at the bottom of it?
That's using the same equation that we just derived. Pressure, now something I've kind of glossed over is it doesn't matter what the shape and the width is. You could have a hose that's vertical and constant diameter, or you could have a big funnel, or you can have a hose that's swirling all over the place. The pressure difference only depends on the difference in elevation. So when I said the pressure is due to the weight of the material above, that's true if it's a clear shot to what's above. If not, what you basically do is you say the pressure at this elevation is the pressure at this elevation everywhere else where air can freely move. And so air can freely move under the door and around and whatnot. So the pressure at this elevation is the same as the pressure at this elevation outside in the open air. And then my explanation is the weight of the air above works out. So I, of course, have by now forgotten your question, Bryson.
Oh, you explained it.
Okay.
I was asking what would the pressure be at the bottom of the dam?
So the pressure at the bottom would just be the density of water, which is 1 well, let's say 1,000 kilograms per meter cubed times G, we'll use 10 there. So 10 meters per second squared, so that gets us to 10,000, times the height, 6 meters. So I would have 1,000 kilograms per meter cubed times 10 meters per second squared times 6 meters. Okay, you can't read the 6 anymore. So that would be 6 followed by 4 zeros. So 60,000, then my units are going to be, notice 2 of the meters canceled, so I have kilograms per meter second squared, or what we more commonly call a Pascal. So it'd be 60,000 pascals higher than the air pressure at the top of the lake. So the air pressure at the top of the lake is atmospheric pressure. I said 14.7 pounds per square inch earlier. In the metric system, it's 101,000, excuse me. It's like 101,300 pascals. So this here, at 6 meters, that's about 60% more than atmospheric pressure. If you go down about 10 meters, then you've increased by about 1 atmosphere in pressure. So if you're swimming and you swim down to 10 meters, which is somewhere around, a little over 30 feet, then the pressure will double. If you go down to 20 meters, you'll go up to 3 times the pressure on the surface. And so that's why things like your ears and sinuses really hurt as you go down, because the pressure goes up pretty quickly.
How did divers get the bends?
Had what?
How did divers get the bends?
Okay, so the bends is a complicated issue that starts with gas in the blood. Right, you have gas in the blood. Right now we're breathing air. We have oxygen and nitrogen, and that's attached to the hemoglobin. And that we have bubbles of a certain size. As you go down, the pressure increases, and that makes the bubbles smaller, right? But then your body will actually, as I understand it, I am not a physiologist, mind you, your body will then adjust to the bubbles, increase to about the same size again. So you actually have more molecules in the bubble now because of the higher pressure. When you come up, because the pressure is now dropping, those bubbles start expanding. And that's where your problems start. Because you have these bubbles expanding and, it's in something that can't withstand that expansion, then it's going to break stuff. So there's no problem with going down quickly. There's a problem with coming up quickly. And I don't know if you see anything about world record free diving or depth competitions where people essentially have an anchor and they hold on to that anchor and get dropped in the water, and they hold on until they get really deep, and then they let go and they shoot up. They don't get the bends because they don't give their body a chance to adjust. They're not breathing in any gas. So the gas in their bloodstream is just staying like it was as they're holding their breath. And so they can come up rapidly without having an issue.
Makes sense.
Yeah, it's dangerous as all get out. I don't know why a person would want to do that. It's like, I think I told you guys, one of my former students has climbed Mount Everest. He's attempted it at least twice that I know of without oxygen. The first time he had to take supplemental oxygen on the way down. I think the second time he was successful. He wasn't successful in summiting this year because he rescued somebody instead of going to the top. But why? Why would you put yourself at that risk? Up there, you're at such high elevation, the air pressure is super low, and the temperature is really low.
What's the difference up there in the amount of, or the air density?
I haven't looked it up. I've only looked up, like I said, it's 70% air pressure where I live. It's still something you can live, where I live, for my house in Colorado is, and it's going to be even lower where Amber's is. Up there, it's very low pressure, which means you have very small amounts of gas that you're breathing in, and it's really cold, and so you can't live there. They talk about it being the kill zone, that top, 1,000 meters or so, that no human can live there. You're dying all the time you're there. You just need to get out of there before you're dead. Why? Let's live in places where we can live. It makes more sense to me. Okay, we're only 2 slides in. Buoyancy, the topic of tomorrow's lab. Archimedes' principle has to do with buoyancy. Buoyancy is the net upward force that occurs because pressure does increase with depth. So in this picture we have let's call it a potato. And the potato is in water, so you have water pressure pushing in on the potato in all locations. But notice these arrows. The arrows on top represent the force caused by pressure. So remember, force is going to be pressure times area. Pressure is force over area, so force is pressure times area. In fact, I will write those 2 equations. Pressure is force over area, so force is equal to pressure times area. So we have on here, pressure equals pressure top. Here we have pressure equals pressure top plus rho GH, because we had change in pressure is equal to rho GH. So there's more pressure on bottom, which means that the force on the surface is going to be bigger on bottom. And so we've learned net force is, mass and acceleration. We've learned to calculate the net force. In this case, there's going to be a net force due to water that's upward, because you have bigger arrows up, bigger forces up, than the forces down on the top. And so that's what we call buoyancy. And in a class like this, we don't go and derive it. We just go to the final equation. The force buoyant is equal to the density of the fluid times G times the volume displaced. So notice it's proportional to the density of the fluid. If my fluid is air has a density that's somewhere around 1.28, I think, grams per centimeter cubed, kilograms per meter cubed. Somewhere around 1.28. Water is 1,000 kilograms per meter cubed. So as I said, water is like 800 times more dense than air. So you're going to have a buoyant force in air, but it's really small because of the low density of the air. But if you go in water, with its density that's 800 times bigger, the buoyant force is much bigger. And so for most humans, the buoyant force, if you're completely submerged, so it's going to be the density of water times the volume of your body times G, is pretty close to the weight of the person, which makes us pretty close to what we call neutrally buoyant. You have equal downward force due to gravity and upward force due to buoyancy. So you can float around in the water, but you can also dive under. If you were more mass for the same volume, that is more dense, then you would have a really hard time staying on the top. You would just go down and you'd have to work really hard to get up.
So if you're really thin, would that make it harder to float?
Actually, no. It breaks down like this. Muscle is dense. So if you're burly, it's hard to float. Fat is lower density than most tissue. And so if you have fat, then it's easier to float. And so you have the combination of your organs and that stuff and your fat and your muscle that determines if you float. So people that have a lot of muscle are going to have a much harder time staying on the surface. So I took life saving with the guy who was a bodybuilder. And he looked like a rock compared to the rest of us because he had a higher density than the rest of us. And as I have aged, I float easier now. Yeah.
So you were saying that buoyancy, it's lower pressure when you're in the air than when you're in the water?
Well, the density of air is much less than the density of water, which means that since the buoyancy has to do with the density of the fluid, the buoyancy for the same object will be much greater in water, much less in air. And what about if you were in mercury? Mercury's density is 13.6 times higher than the density of water. Pretty close, right? Because you would have an upward force. If you were completely submerged, that would be like 13.6 times your weight. So if you were completely submerged in mercury, you would go shooting up. Right? You would shoot up with over 10 G's of acceleration if the mercury wasn't opposing you by its physical force. We call it viscosity.
Do you think when Jesus walked on water, he changed his density so much?
I'm so dead.
That's an interesting question. I've seen people make silly arguments like, there were maybe hidden stones. Come on, that's ridiculous. I tend to think that it's just a miracle. I think Jesus could have walked on air too. Not that he actually made the water physically change so that a normal person could stand on it.
But I mean,
Go ahead.
I don't know. I kind of like that way of thinking.
Did Peter walk on the water?
Yeah, well, I think once again it was just a miracle. I think that Peter could have stood here, and Thomas, the doubting Thomas, could have stood beside him, and Thomas would have gone down. Peter would have stayed up here because I think it was more God holding him up than the water holding him up. But it's pure
He
conjecture.
did make an animal that could walk on water, just not a human.
Okay, animals that can walk on water.
Aren't you?
The
I'm just
spider.
saying.
Water striders can walk on water. That's why they're called water striders. I'm sure they have
But
another
it's
name.
their weight. Like, they don't weigh that much.
Well, it's a little more than that. It's something we haven't talked about that I'll talk about anyway because, we can't cover everything. Like, we didn't even cover chapter 4. Anybody notice?
Yeah, I know. We see.
So water striders can walk on the water because Huh?
I'll look it up.
Okay.
See what it looks like.
it looks like a big mosquito. They can walk on the water because the water has what we call a surface tension. The water wants to stay touching water. And so to break the water apart, it takes some force. And so it acts like tension is on a string. And so when the water strider puts its foot down here, it pushes the water out where its foot is, and the water pushes back to try to not break apart.
So does it
And the pressure it's putting down is small enough that instead of breaking the water apart, that surface tension holds it up.
So it's like a wave in a way? Like, but just not a wave?
Not a wave. It's kind of like a tightrope walker. Right? If you have a tightrope walker, you have a rope, and they stand on that rope, and the rope sags because they're there. But because the force of the rope is always going parallel to the rope, because it's sagged, the rope is pulling up on either side. And it's that upward force on either side that's holding the tightrope walker up. But if the rope isn't strong enough, then the rope breaks and they fall.
So you have to be tight.
Yeah, you have to be, because the strength of the water is not that big, right? And so when we step on it, we just break it apart and go down. But they have a low enough weight that they keep the water molecules from pulling apart. Well, that's not enough to push the water molecules apart. So that's how they can walk on water, which is totally awesome. And you know how you can totally drown one of those things? Okay, there's the brute force method. Just push a little bit. That's what I did when I was a kid. Because I was, I told you about the cat.
You're so mean.
Well, I wanted to know what's going on. And I was like, so are they floating? Because if they're floating, I should be able to push it underwater. It should just come right back up.
It didn't. Did
No, it didn't.
You killed it.
I did.
What if it was a mommy? What if it had like babies? You
Give me
killed
any
all
kill
of
here. I feel bad enough for all the experiments I did on animals as a child.
You killed
I
all
wasn't a
of them.
sadist. I just
What's
didn't
the
know.
worst experiment you did?
It was the cat. I mean, it's not like I damaged
Well,
them.
that's not too bad.
But still, it wasn't very humane. It didn't cross my mind about this hurting the cat. I was doing experiments. So where are we going with this?
But we were talking about because they could
Oh,
walk
yes,
buoyancy,
yes.
and he thought Jesus changed his mass.
He did.
Yeah.
He changed his mass so much that he
So
had
he
to break the
could walk
surface
on
tension of the water.
Okay. If you put soap in a liquid, soap, as we'll learn when we do the chemistry section of this class, is a surfactant. It lowers the surface tension of the water. It makes it so the water is easier to break it apart. And so if you put soap in the water, what happens to the water strider?
It sinks.
It sinks. Is that horrible? I've never done it.
Did you do that too?
No, never done it. But you know, it would obviously depend on the water strider if it's going to sink or not. But potentially, you could put soap in the water, and the water strider then sinks.
So then,
And says, "What in the world?"
so then if you mix water and dish soap and have oil on top of that, will the oil start to sink when the water and dish soap are mixed together?
Well, and once again, when we get to chemistry, we'll be talking about this. The soap has a polar end and a non-polar end, and one end will attach to the oil, one end will attach to water, and so it kind of holds on to water, or holds on to oil and then holds out to water, so it'll pull it away from whatever you put in there. That's the actual purpose of soap. And not just oil, but grime and other things. So, yeah, it dissolves oil because it holds on to the oil and holds on to the water, so the water will pull the oil away. And so it helps you to mix water and oil, because normally they don't mix.
So
Yeah.
for the test, are you gonna give us like word problems with numbers, and we're gonna have to figure out what the force of buoyancy is?
Okay, so you will have a few problems that will require you to do that. You will have all the equations, right? You don't have to have any equations memorized,
Oh, okay.
but
so
you
we
have to be able to use those equations.
Okay. Okay, because it's so hard memorizing all.
Yeah, and
of them.
memorization, at least in physics, we really don't hold memorization in high esteem. We figure anyone with half a brain can memorize if they decide they want to. But what we really hold in high esteem is the reasoning, the thinking about why, what's happening. And so the most of your questions will not be calculation. They will be asking you what's going on here, why, what's going to happen. And remember, half your questions are going to be ones that you guys write. And so, you know, your quiz questions are all questions you guys write. So you should get a feel for what kind of questions your classmates write. All right. So Archimedes' principle. Now that I've talked about buoyancy through and through, Archimedes' principle is kind of a downer, but it's always good to tell the story of Archimedes. Do I have a pretty picture? Nope, no good picture of Archimedes. Okay, so Archimedes, the story goes that the king had some gold, and he sent it off to let's call it a goldsmith, I think that's the right word, to craft it into a crown for him. And he gets the crown, and for some reason, he thinks that the goldsmith that he hired cheated him. That this goldsmith kept some of the gold for himself. And so he comes to Archimedes and tells him, I fear that I've been cheated. I want you to be able to determine if I was cheated or not without destroying my crown. Because if I wasn't cheated, it would be a shame to destroy the crown. But if the crown's not solid gold, well, then by golly, that guy's going to die. So Archimedes thinks about it. And of course, you have the obvious things. I gave him 1 pound of gold. Let's weigh the crown. That weighs the right amount. But that's not proof. That just says it weighs the right amount. But you can put rocks in there to get the right weight. And so Archimedes is thinking, finally, draw me a bath. I think best in the bathtub. So bathtub is filled. And as he gets into the water, he recognizes, hey, as I get in, the water level rises. Voila! Hey, I'm sure you said that. Actually, Eureka is what they usually say. Eureka, because that's the California state motto. We have a long motto. Eureka means I found it. And he jumps up and goes running down the street butt naked and don't put butt naked as part of your, potential test question. That's not relevant. Excited that he had figured out how to do this. Because what he realized is when you get into the water, you move water out of the way. And so if you measure how much water you move out of the way when you get into water, that tells you what your volume is. Right?
Yep.
And so if you take the crown and you completely submerge it in water, then the water level changes by a volume equal to the volume of the crown. And if you measure the mass of the crown then you can take the mass of the ground divided by the volume of the ground, and that will tell you its density. Gold is very dense. Anything as dense as gold is going to be more expensive than gold. So he's not going to be able to have a density as high as the density of gold if he puts something else in to replace gold. And so as the story goes, he does the test. The crayon's density is too low. So they cut it apart and they see that he had formed a framework for the crayon using grass that he weaved together, and then just folded the gold over it to get to the right weight and kept the rest of the gold. So I'm sure it's off of his head. I mean, what else are you going to do with somebody who's going to cheat the king like that? The whole point of the story is how we come up with Archimedes' principle, telling us that in the end, the weight of if something is floating, the weight of the fluid displaced will equal the weight of the floating object. Or if something sinks, the weight of the fluid displaced is equal to the buoyant force. And that's usually the way we treat this for a class at this level. We say Archimedes' principle, the weight of the fluid displaced is equal to the buoyant force. So in our lab tomorrow, we're going to measure the volume of water displaced, multiply it by the density of water to get the mass, multiply that by g to get the weight of the water, and then we'll use that as the buoyant force in our calculations. So, of course, it's important to have gone over Archimedes' principle before we do it in lab tomorrow, or else you're going to be sitting there like, well, golly, I don't know. I'll make something up. And, yes, I'm just going to skip over that. I've talked about it. On which of these blocks submersion water has the buoyant... Wow, that's not even English. Which of these blocks submersion water has the... Yeah. There. Now that we've translated into working English, it should have been on which of these blocks submersion water is the buoyant force greatest, but it doesn't make sense the way it is. Let's just go on. So if we have 1 kilogram of dense material, 1 kilogram of low density material, or 1 kilogram of super dense material, or are they all the same? Okay, I have 2 answers for C. Okay, density is the mass per volume, right? They all have the same mass. That means their volumes are going to be different. The least dense one has the biggest volume. The most dense one has the smallest volume. What does the buoyancy depend on? Well, it does depend on density, but that was the density of the fluid you're floating in. All of these are submerged in water, so the density of the fluid is the same for all of them.
It depends on the volume displaced.
So it depends on the volume displaced is the other thing. So the density of the fluid is the same for all 3. Which one's going to displace the most volume? B. Hence, B is the one with the greatest buoyant force. Right? The question required you to do some analysis here, some thinking. It's not just a straightforward. And like I said, it's not like we're trying to trick you in physics, but we want to make sure that you're reasoning the ideas through, right? It's not just I can memorize something, which is, to some people, disappointing because memorization is easier than the alternative. All right. I am going to, I should mention with this as well, floating. So things will float if their volume is bigger than the volume of water that would weigh the same as them. Or to put it another way, if an object is less dense than the fluid, it will float. So wood will float, most wood will float in water because the wood is less dense than water. Whereas iron will sink in water because iron is more dense. If I put the iron in lead, lead is more dense than iron, so what will happen?
Sink even more.
Because the object is less dense, it floats.
Oh,
That's actually why hot air rises. Hot air will try to expand. And if it expands, that lowers its density because you have bigger volume for the same mass. And so hot air is less dense than cold air, and hence it floats upward. So how does a boat float? Boats are made of typically iron. Iron's more dense than water. How does a boat float?
it has to be big so it covers more water.
Right, because it's displacing water, and the water displaced doesn't have to be just the volume of the object, it's the volume that it's pushing out of the way. So if you were to drill a hole through the boat here, so it filled with water, it would sink because it's a more dense material. But because it's displacing more water, because it's hollow, that's why it can float. So it has an effective density that's the volume that it's displacing divided by its mass, or mass divided by that. Okay, we got to stop here.